Hi, welcome to the unit circle in trigonometric functions. The unit circle we had a little bit of a look at before, and I've drawn a diagram here for you, just showing you that the unit circle we usually think of as centered at the origin 0, 0 with a set of axes, x and y axes here, and a 1 unit radius. So this point out here is 1 0, out here is neg 1 0, up here 0 1 and 0 neg 1, simply meaning 1 unit radius. So in other words, y on this diagram is going from neg 1 to 1 and x is going from neg 1 to 1. So we're going to be working with this and looking at trig functions, and there's going to be an explosion in this presentation. Trig functions are going to actually explode and go into a whole new realm called circular functions. A bit of excitement down here. This little diagram is just trying to remind you that if you have an angle equivalent to pi, it would be equivalent to 90 degrees in a unit circle, then the arc length over radius would be pi on 2 over 1. So the arc length will actually equal the size of the angle, if you like to think of it that way. And then this is a bit of an interesting one. We're wrapping a number line around the unit circle here. Hey, we'll have a look at that later on, I think. Too much all at once. Let's come down and have a look at trig functions here. So I've drawn a circle here because we're going to be working quite a bit with that. And when I say trig functions, I just hope that you think, I remember something like SOHCAHTOA. I guess that's what most people think about. What they learn in school about the ratios, and that is in any right-angled triangle, here we are, we're going to draw one now. If I have an angle theta, this is the opposite. Remember, you go to the angle, look out. That's the opposite side. Go to the 90, look out. That's the hypotenuse. And then this one must be the adjacent. That's probably the easiest way of remembering those things. And then SOHCAHTOA helps us say that the sine of angle theta will be the opposite over the hypotenuse. That's the first result. And then cosine of angle theta is, let's look at it there, those two, is the side adjacent over the hypotenuse. Do you remember this? And it's handy, isn't it, to work out missing sides and angles. The tangent of angle theta is equal to the opposite, here it is up here, opposite over the adjacent. Okay, so all good stuff from before. This is abbreviated usually SIN, cos and tan. Okay, you might like to look up the origins of those words. It comes from Arabic investigations. And it's interesting to see how those names have evolved, but we won't be going into that here. So this is what we usually draw. So can we come across to this unit circle? See, it's 1 unit here as before. I've got some other scales in there, 0.5s and stuff. Can we come across here? And what I'd like to do is to just put this right-angled triangle idea into the circle. So I'm going to draw an angle of 30 degrees here. So we'll just draw this across now. See if we can do it reasonably accurately across there. And then we come down here and complete it and make that 90. So this angle is actually pretty accurately 30 degrees here. Or you could be thinking, hey, that's pi on 6, isn't it? So I'll put that in brackets maybe. Pi on 6. Now, can we find the sine of this? Okay, well, this is a 1 unit radius circle, so let's do it over here. The sine of 30 degrees is the opposite over the hypotenuse. So what's the opposite? Oh, that's this side here. So that is, oh, that's interesting. How high up is that? Here it is there. It's 0.5. Okay, it's 0.5 over the hypotenuse. Oh, it's 1, because that is the hypotenuse across there. So it's 0.5 over 1, or just 0.5. Hey, this is interesting. In a unit circle, that's just equal to the y-coordinate of that point P going around the outside there. If we think about creating angles this way, this P's got an x and a y, and if it's a 1 unit radius for the hypotenuse, okay, 1 unit radius of a circle, therefore the hypotenuse is 1, it's just the y-coordinate. Let's do the cosine of 30. That's the adjacent over the hypotenuse. What's that? The adjacent. Let's just rub this one out here. We don't need that for the minute. The adjacent is this. A bit of a squiggle there. The adjacent is this side. And how far is that? We can't read this exactly. It's a decimal, but it's the x-coordinate, isn't it? So this one is the x-coordinate over the hypotenuse, because it's a 1 unit radius circle, it's 1. This is interesting. In a unit circle, the SOHCAHTOA stuff becomes a lot easier. Hey, this could be a good place to work. In other words, this point here, going around at the end of the angle 30 degrees, its y value, y is the sine of the angle, and the x value is the cos of the angle. That could be interesting. All right, well, if we do that, well, what's tan? Hang on, we better do tan. The tan of theta is the opposite over the adjacent, which is equal to, the opposite was this value, was the y-coordinate over the x-coordinate. Oh yeah, well that's okay. Oh, that's also equal to, therefore, sine theta on cos theta. So that's a nice little proof that tan theta is the sine over the cos. Hey, this is developing quite nicely. Well, what else can we do? Oh, well, if we kept going, we could have 60 degrees, 90 degrees. Hey, that's where trigonometry stops, isn't it? Trigonometry is about right-angled triangles. But if we have a new definition, that is, the sine and the cos are the y and the x coordinates of point P travelling around the circumference, then we could keep going, couldn't we? Why stop now? Why stop just because it's bigger than 90? Let's go over here and put up a matching one over here to 30 and draw it down again. What would that be? Well, if that's 30, there they would be all lined up, wouldn't they? We could create another point here, call it P1. Now, P1 would have what would be its x and its y. Hang on, I'll put the y in because we know the y is 0.5, goes right through there. So the y is 0.5. The x value here would be the negative of this one. They'd be symmetrical, wouldn't they, if this angle was 30? So this would be the same x value, no, it'd be minus x, wouldn't it? Because it would be negative. We're going in the negative x direction here. So is there any value in that? What have we just done? Well, let's have a look. What is the angle now that we've traced out to get to the new position of P? Well, it's 30 back, so these triangles are congruent and match. That is 150 degrees, isn't it? So we could say the sine of 150 degrees is the y-coordinate, which we can see exactly is 0.5, and the cos of 150 is the x-coordinate, which is negative the x from this first triangle. Oh, this is interesting. It raises the possibility of having sine, cos and tan of angles bigger than 90, which is not possible if you restrict it to a 90-degree triangle, as we do in trigonometry. So this is our new definition. So let's look at this. This is our new definition of sine and cos, and this work, when it's done on a circle, is really referred to as circular functions. Now, conventionally, nobody makes that decision. Usually we just stay with the word trig. But there is really a very important difference between circular functions, when we've extended trigonometry to go outside 0 to 90, which is what's in a right-angled triangle. So we're now dealing with circular functions defined on a unit circle. So we could keep going. Is there another one equivalent down here? Yeah, well, if we go down here and made that 30 in there, so can we tidy this up a bit now? Let's just tidy all of this up a little bit and keep the one in the first quadrant or quarter of the circle, and we'll tidy this up. So now let's draw an equivalent triangle through here. So it's all going to be symmetrical. So this would be 30. So that the original triangle, so we just tidy this up. I'll just go back to this. So now, if I put point P back in again, and that came to exactly 0.5, we don't know what that is exactly there. So if that was 30, now there, and this is 30, what can you say? Well, the hypotenuses are equal, and they've got a 90 in each, and they've got another angle. So that's two angles and a corresponding side. These two triangles, let's call this P, this is down to P2 now, we use P1 back up here. These two triangles, this one and this one, are congruent. Therefore, this y, that length there, which was 0.5, is going to be equal to this one here. But it's going to be negative, isn't it? Gone downwards. And this x here is going to be equivalent to this one. This is going to be neg x though. So what are we doing? Well, we're creating positions where you can find the sine and cos of bigger and bigger angles. What would this one be though? If we went right around there, it would be up to 210. So we could say the sine of 210 degrees is what? Neg 0.5. Going to have the same value because of the symmetry of this triangle and this one. And what would be the cos of 210? It would be equal to neg x again. They can be matched up due to the symmetry there. Can you keep going? Well, yeah, I think we could keep going across here and do another triangle which would match again as long as we kept the angle in here now as 30. And so let's go down a little bit here. This time, what would our rotation be? It'd be right around here, be 330 degrees, 30 degrees back from 360. So we could have the sine of the big angle 330, which would be, under our new definition, the y value of this fourth point here, third point, sorry, when we start off with P3. So sine of 330 is the y coordinate, which is again neg 0.5. And the cosine of 330 would be back again to whatever that x value is here in the middle, the x value that we use there. We didn't read it off because can't read it off exactly. We're going to investigate that later on. What an explosion! What an explosion into circular functions. We can actually keep these sine, cos and tans going right around the circle. Okay, so circular functions now are the SOHCAHTOA stuff, circular functions, the SOHCAHTOA sine, cos and tan extended to a circle. And the new definition is the sine of theta is the y coordinate of the point P travelling around the circumference. The cos of theta is the x coordinate of P, and the tan of theta is the y over the x. What an explosion! This is typical of mathematics. We started off with an idea and now we have expanded it. Remember, it does incorporate trig functions because the trig function work in a right angled triangle is still consistent with this. We've just made a big extension to it. Okay. Well, do you want to look at something interesting? We'll just go down a little bit more with these circular functions. If we looked at the unit circle again, just draw it down here, I messed up that top one. If we drew that again, and this is 1, this is 1, and when we draw this here, what do we always get? If we draw a right angled triangle, got an x value and a y value, so this distance in here would be the x value, this distance would be the x value, and this would be y, and the radius would be 1 unit circle. So something interesting is going to happen there. By Pythagoras, what do you notice? X squared plus y squared equals 1, which is actually the formula or equation for the unit circle, as that's a rule that x and y must obey if that point P is going to travel around a unit circle by Pythagoras. But also, what's interesting, x is the sine of theta, so sine squared theta, sorry, that's not right, put the wrong one first. X is the cosine of theta, so cos squared theta plus y is the sine plus sine squared theta equals 1. We've found an interesting result by coming into that unit circle. Cos squared plus sine squared must always come to 1. That's interesting. So what are the two bonuses here? We've got many bonuses. This is the equation or rule for a unit circle, for points to lie on a unit circle, where a circle radius equals 1, about a centre naught. And also we've found this result. Hey, this is busy stuff. This is interesting, and that's what we're going to build upon now. The idea of circular functions. But as Pearson's mentioned, and there are screen clippings now coming from Pearson's textbook, as Pearson's mentioned, we still generally just refer to them as trig functions, sine, cos and tan. But they have actually exploded into a new dimension called circular functions. Let's go on and see what you think as we develop this idea. All right, so what does that mean? What flexibility have we got now? Well, we could take a number line, any number, and wrap it around the circle. So this is called the wrapping function. I think Pearson's refer to this as a wrapping function. So you could actually wrap that around the circle, and depending on where it landed, of course, now this is the arc length and radius idea. So if you have a length here of 2 wrapped around, that'll be the arc length, but that will also be the size of the angle in radians, wouldn't it? Because radians are arc length over radius, and the radius here is 1. Okay, so you'll wrap a piece of line around and you'll create the idea of an angle. But you could also have the x value is what now? The cos of the angle. That'll be cos of t. And y is the sine of theta, or sine of t. Hey, this is getting crazy. We are talking about finding the sine and cos of numbers on a number line because of circular functions, and just wrapping that around and using the idea of radians being arc length over radius, then we've got a direct association between the angle, okay, just write that again, between the angle at the centre, so this is equivalent to our angle theta as we used to. Okay, used to say. But we could call it t now, because it's going to have the same value as the arc length. Crazy, crazy. Yeah, you're going to see how this develops into some really good mathematics in modelling, as I mentioned in the last presentation. We're going to model some behaviours, and it's going to be very useful to be able to work with just ordinary numbers. Why are they negative? Because we're going to wrap this way. And remember what I said in the last presentation, we have a convention when we're using this to represent angles. If we're going this way, it's positive. We're going clockwise, it's called a negative rotation. So we're starting to look at movement around a circle in two directions as well. So an interesting explosion. You might have to just stop and rewind the presentation and think through that a bit. All right, let's see what we can do in developing it. What have we got now? We've got trigonometric functions sine, cos and tan, which are really circular functions. They have exploded. Circular functions, really speaking, but as Pearson says, in all the literature, we actually don't make that distinction much. So, if you have any real number and it wraps onto a point on the unit circle, then here we have the definitions. You can find the sine, cos and tan of any point, any value, because you can think of that value as being wrapped around the circle. So let's summarise what's happening. In the first quadrant, x, which is the cosine, is positive, y is positive, and so y on x would all be positive. So they are all positive in that first quadrant. As you go round, you'll notice here the sine, which is the y value, is still positive up there. The cosine, which is the x value, has now gone negative. Yep. And the tangent, which is y over x, will be a positive over negative. That will be negative. So the only thing that's positive in this quadrant is the sine. So we're going to have mixtures of positive and negative as we land in different quadrants of the circle here. So this is called the first quadrant, the first quarter, second quadrant, third quadrant, fourth quadrant. And down in the fourth quadrant, the sine is the y value. Yep, that's gone negative. The cosine is the x value. Yep, that's on the negative part of the number line there. And the tangent is y over x. That's a negative on a negative. So tangent is the only one positive there. So this is SA, T, and what's the last one going to be? Well, the sine here is the y value, so that's going to be negative. The cosine is the x value, so it's only the cosine which is going to be positive there. Why? Because the cosine is the x value. Okay, so we're going to get fluctuating signs, pluses and minuses, as we go around the unit circle. So here's the definition of circular functions hiding down the bottom here. On the unit circle, if we land on a point P going around the unit circle, then its x value is the cos of t and y is the sine of t. So they depend upon where that line terminates, where the arc terminates here, in what quadrant, because your P, x and y's of the P are going to vary. Interesting stuff. It does get better. Don't get too confused at this stage. Let's go down and have a look at some hints here. When sine, cos and tan are defined as circular functions based on the circle, we usually use radian measure. You don't have to though, right? Do you remember? You've got to be flexible. I just did this right up there with my circle. I said you could have 30, and it's still circular functions, because if you make that 30, it's equivalent to the angle of 150, and that's the notion of circular functions, not just radian measure. The initial notion of circular functions is that the y value is the sine, the x value is the cosine. And when we went across here, we found the x went to neg x, that neg x value, y stayed the same. So we could talk about the sine, cos and tan of 150. That's really the basis of circular functions, and that is that the sine of the angle is equal to the y value, the cosine of the angle is the x value of that rotating point, and the tan of the angle is y over x. You don't necessarily have to be in radians. It is more general though. This is true, it's more general, but the basic circular function notion is this one here. Okay, so here the values for the domain and range of the cosine functions are real numbers. They're arc lengths on the unit circle. Yep, you don't have to have degrees. You can have radians as arc over radius, which is just the arc length, because radius is 1. The arc length on the unit circle subtends an angle whose radian measure is equivalent to the arc length. Yep, well, we know that now, because as you go around here, if you have a distance t, the measure of angle theta in radians is arc length over radius, which is 1. But that's what they're getting at. The measure of the angle theta equals the arc length. So you can call that t, if you like, in radians. Okay, are you flexible? All right, come on down, let's look at developing this and why we're doing it. Here's a comment from Pearson's. We're surrounded by periodic functions. And what does that mean? A few examples include the average daily temperature variation during the year. Okay, it cycles, in other words. It goes up and comes down. And it keeps following a pattern. It repeats itself, periodic. Sunrise and the day of the year. Okay, on a particular day of the year, the time of the sunrise will cycle. A year later, it will be back at the time of sunrise again. It's going to cycle around. Animal populations, the height of tides, position of the moon, temperatures from season to season. Here's an interesting one. Your height above the ground when riding a Ferris wheel and rotation of the wheel. Why don't we have a look at that one and see what that is like. Here's the Ferris wheel. And here we've tried to represent what's going to happen to you. Okay, so here, let's say just go up here a little bit. Oops, and too far. Let's just come down here. We've got a few problems here. Let's just do it slowly here. So where would you be if you are starting on the Ferris wheel? Let's start you over here. So that would be equivalent to here. You go up to your maximum point, then come down at this horizontal position there, and then you come to your lowest point, closest to the ground, then you're going back to the horizontal position and highest point. So you've got a principal axis, if you like, above which you're going above and below that point. You've got a maximum and a minimum. This is called the amplitude, how high up from that central position you go and how low down. And the period is deemed to be how long it takes to get back to that same point. So you've gone up to there, and then you're coming around, you're going down and then back to the position. So this is back to your starting position, returned again. So the period, or the time it takes to complete a cycle, is that. So that's an interesting problem we might want to model, and you'll see something right now which is going to be exciting. Here it is here. What is this? Do you see? This is the graph of sine x. And I've gone back to degrees so you can see the rotation idea. So as you go up on the Ferris wheel, let's start you here. As you go up, and that's that value there, the y value, we're plotting the sine, so that's the y value of the point P on the circumference. So how far up have you gone over here? Plot it there, then go a bit further, plot the y value. Can you see it's going to work? the maximum there of 90 is 1, using a unit circle to what? Model the Ferris wheel. Okay, and then as you come down, the y value will match the previous y value. Why? Because of the congruent triangles, remember that? So this is a perfect function, sine, to model that behaviour. And these match down the bottom, don't they? Only they're the negatives. Right? Because as you go around the unit circle, you get what we call periodic behaviour. You get a repeat of the values. And so this is one period or one cycle of the function sine x. We could have guessed that, because once you did one revolution and came back here, if you did it again, you'd repeat all those values. You should be able to keep going. Remember, you're dealing with circular functions now. They don't stop at 90. You can keep going. So after you come back to your starting point, you've gone around 360 degrees, but you can keep going. And what's going to happen? It's going to repeat itself. This is interesting. An interesting function. The circular function of sine x and cos x. All right, let's go down and have a look at the definition of a periodic function. A periodic function is a function such that if you add a value p to it, you get the same value. For all p's though, for all x's, it's got to work. P is the least positive constant for which you get a repeated function value. So you start with a value and then p later, then you're going to get the same value. What would p be? What is p for sine x? What is it from what we just did? Do you want to come back up and have a look? What do you reckon? How long before it repeats itself? Can you see it? It is 360 degrees, or in radian land, 2 pi. It's going to repeat itself every 2 pi. It's a perfect function to describe the rotation of a Ferris wheel. Okay, let's go down. You see, we're going to be doing some interesting maths here. Let's do some examples and then let you loose on all this stuff. All right. Evaluate the sine, cos and tan functions for the following values of t. So they're thinking about arc length around the circumference in a unit circle. So when t is 0, let's go down. Well, you can read this later on if you like. Basically, we're talking about the sine of t being the y coordinate, the cos of t is the x, the tan of t is y over x. When you are tracing out along here, t if you like, and it's the point p, x, y. Just going off the page here a little bit, let's just put it up here. So if we go here, okay, so we're going along there, t or t in there because it's a unit circle, and we have a point P here, x and y. That's what we're talking about. Okay, so if you have t as 0, you've gone nowhere. You've gone there. So the angle is, or we're at the point 1, 0 if you like, on the xy axis stuck in there. So what's the cosine is 1, the sine is 0 over here, and the tan is 0 over 1 or 0. So we're just going to use a circular function approach instead of SOHCAHTOA. What about pi on 2? Pi on 2, or 90 degrees in there, wouldn't it be? Pi on 2, a quarter of a circle. Or you can say pi on 2 is equivalent to 90 degrees of rotation in there. So you're up to here, and that, using the x and y axes, is x is 0, y is 1. So the sine is the y value, is 1, and the cos is the x value, is 0. And the tan of pi on 2 is 1 over 0. You can't define a tangent of 90 degrees. Alright, let's come down and do the next one. What about pi? Length of pi. Well, that's half a circumference if you like, doing it that way. Or you could think of pi as being equivalent to 180 degrees in the centre. thinking about the arc length over the radius. The two will be the same because this is a unit circle. Unit circle. So pi in the centre, or 180 degrees, and pi is going to be the arc length. So where are you going to end up? This is the x and this is the y. So the sine of pi is 0 and the cos of pi is -1. Pinching the x and y coordinates. The tan of pi is y over x, 0 over -1. Do you get it? It's becoming quite different, isn't it? Okay, not hard though. We're just developing this with the arc length and radius stuff and expanding trig functions into circular functions. 3 pi on 2, can you find it? Well, 3 pi on 2 is equivalent to 270 degrees. That might be the easiest way of finding it. So your point P is this one here. So the sine of 3 pi on 2 is the y, which is -1. The cos of 3 pi on 2 is the x, which is 0. And the tan is 1 over the other, which is undefined because you've got 0 in the bottom line. What about 2 pi? Oh, I think we're back to the beginning. Didn't we say the period was 2 pi for sine? Oh, it looks like that's a period of cosine as well, because in one revolution you're back to the starting point. And so the y value is the sine of 2 pi, the x value is the cos. And they've both gone back to the beginning. So the period is 2 pi for both sine and cosine functions. Okay, the tangent is y over x is 0 over 1. You might like to start thinking, what is the period of tangent? Is that also? I don't think so. Let's go back up. I don't think that's also 2 pi, is it? There's an undefined tangent. And then later, and then a tangent of 0, then another undefined 1, and then a tangent of 0. Things seem to be happening more quickly for tangent. Anyway, we'll come and look at that later on. Let's go down. Okay. Domain and range of trig functions. That's what we're starting to talk about, isn't it? So here, what is the domain and range? Let's have a look first of all at the domain of these functions. Well, you can see we can keep wrapping. Wrapping function. Keep wrapping around here. Okay, no music in that one, mate. Different sort of wrapping. Oh well, all right. So here, you can keep wrapping either direction. So you can find the sine of t or the cos of t for any t. So the wrapping function, the domain is the set of, let's say, x such that x is a member of R. Don't confuse the x's here. We usually say y equals sine x or cos x. Well, we're using t here because we don't want to confuse it with the values on the x-axis. But here you can have any real number in sine x and cos x. Any real number in there. Okay, we might have to watch tan though. What is tan? What is the domain of tan x? Tan x, because it's y over x. We can't have any angle which gives you a x coordinate of 0. So what points are those? Well, therefore, they are when the angle, let's say, so I'm confusing it here with the angle. So the angle cannot be equal to what? Well, where was the x value? 0, pi on 2, and 3 pi on 2. So we found that before. But we really should go back to putting t in here. I think it's going to get a little bit confusing if we do that. We'll just put t here as our function, sine of t, cos of t, so that here you can see that that's the angle and this is the x coordinate of the point. And when the x coordinate of the point is 0, is at pi on 2 and 3 pi on 2 or neg pi on 2. So here you would have a domain for tangent would be equal to the set of t such that t is a member of R, but t is not equal to pi on 2 and 3 pi on 2, or we might have to say more. That's only on one revolution, but it would be no multiples of that. Okay, t is not equal to multiples of this. So k times pi on 2, 3 pi on 2. We'll come back and have a look at that in a minute. All right, so what about the range? What about the range? The range is the set of y values. Now, with this, in the unit circle, sure, x only goes from -1 to 1, so that's the values in the x-coordinate here, but we can actually wrap around for sine and cos of t, any value for t. We can wrap around here because we're talking about t being around here, but how big can x and y get, the coses and sines? Well, the y value is the value of the range, or the value of sine of t, and the x value is the value of cos of t. So the range statements would be like this. Is a set of values here of y such that y, oops, I've gone past it now, y is between -1 and 1. Isn't it? Because the x's and y coordinates here, the sine and the cos, are both between 1 and -1 and 1. So that's the range statement for y if we're calling y equal to sine t or cos t, not confusing it with this y here, which is the y coordinate of the point. So the range of the function, you can't get a value bigger than 1 and you can't get a value smaller than -1 for either sine or cosine, because it's locked into the unit circle here. All right, let's go down and see what we can summarize here. And here's a bit of a summary. Domain and range. So the domain of sine t and cos t can be any t. The domain of tan t cannot be pi on 2 or multiples of that. So one way of doing that is you say, well, you can't have pi on 2 and you can't add another pi to it. Let's do that here. So when you get pi on 2, the values of this point are 0 and 1. So cos is 0 and tan is sine over cos, or y over x, so you can't divide by 0, and that's at pi on 2. And if you go pi later, then you get another point, which is a problem down here, which is 0, -1. So these are the points where tangent won't exist. Any pi on from a pi on 2. So if you go another pi, you're back to this problem. Okay, so that's what we're trying to say there, and k is a member of a set of integers, so it could be positive or negative. We could move either way around the circle, so you could say, well, let's go here pi on 2, so that's there, and we got a problem. Then if we took away pi, so z would be -1, took away pi, we came down, this would be neg pi on 2 now, coming down this way. Then we would still have this problem. The cosine would be 0 and tan would be undefined. Okay, so let's have a look at that. Then over here, the range is between -1 and 1. Notice they've used f of t to avoid the confusion as we had earlier there with the y value being the y value of the function, or the y coordinate of going around the circle. And the thing about tangent is that because it's sine over cos, you can actually get a whole range of function values for all those values for which tan is defined. So if it's on the domain of tan, you've got a sine over a cos. Let's put it here as sine t on cos t, our tangent. Now, cos of t can be anything from -1 to 1. Okay, so if it goes up to, let's say, something like 100th, and dividing by 100th gives you a large number. You can reach very large numbers, any real number in fact, with this division of sine t over cos t, provided that cos of t is not equal to 0. So what have we got then? Basically, these statements here are describing the behaviour and the period of these functions. So sine of t is the same as sine of t plus any multiple of 2 pi, where k is integer. So you can add on 2 pi, so let's take this value here, for example, this angle or this arc. If we go 2 pi further, we'll be back there again. Or if we went negatively 2 pi, we'd be back there again. Okay, so here k could be a positive or negative whole number, multiple of 2 pi, and you'll spin right round the circle back to the same point again. So you will have the same value. So that's why 2 pi, we said before, was the period. But this is the technical way to write it now. Cos of t is sine of t is a cos of t plus the multiple of 2 pi. The period is 2 pi. And any whole number, positive or negative, rotation around the circle, will bring you back to the same point, give you the same cos. Now, we mentioned earlier tan is going to be different because we found that it was repeating itself every pi. Okay, because y on x, in the unit circle over here, let's have a look as we go out here or out here. Our y on x value, here and here, okay, our y on x value is going to be, first of all, a positive. Let's just go back up there. So here, our y on x value, y on x is going to be a positive, then it's going to be a negative, and then it's going to go back to positive and negative. So can you see, as we go round here, the ratio is going to come back to the same value here as what it is here. So it's got a period of only pi before it repeats itself, including the point where it is undefined. Tan undefined at pi on 2, because you're dividing by a cosine which is 0, and then the same thing's going to happen down here, pi later. So it's actually got a period of pi, and here we're saying, remember, it's a whole number lots of that period. So the smallest number to repeat itself is pi, but every time you go pi further, you'll get a repetition. Remember, it's positive or negative whole number lots of the period will take you back to the same point. All right, let's go down and work with some actual angles. So here we are. What about finding the exact answer for something like pi on 4? We did it with 0 and pi on 2 and 3 pi on 2 because they landed in nice positions here. It was easy to work out the x and y coordinate. But here, t is pi on 4. Oh, that's going to be interesting. Pi on 4 is exactly halfway. Let's see if I can draw this accurately now through here. So we're going to go through halfway and see if we can just pick that up. About like that there. Not quite right there. But we're going to try and draw pi on 4. It's something like that. And our point P has an x value and a y value. We come down here, and that shouldn't be right on a value there actually. and it should be just past it. So I haven't drawn it perfectly accurately. So pi on 4, how do I know where to do it? It's halfway, isn't it? Pi on 4 is half of pi on 2, or if you want to go back to old degree land, it's half of 90 is 45 degrees. All right, okay, so what do we know? This is a 1 unit radius here. Now in 45 degrees, that will also be 45 degrees. So these two sides form an isosceles triangle, and they will be equal. So let's call it a value. What can we say? Let's say the value is what? N, and this is n. So can we find these values? Because these are the sine and cosine, and they'll be the same, won't they? So by Pythagoras in here, we've got the square on the hypotenuse equals the sum of the squares on the other two sides by Pythagoras. So 1 equals 2n squared, or a half equals n squared. So here, plus or minus 1 on root 2 equals n. Now in this quadrant, you can see they're both positive. So for quadrant 1, x is 1 on root 2 and y is 1 on root 2. So we've just found the sine and the cos. Because it's 45 degrees, they're both equal, and we've used Pythagoras to find it. So let's put it over here. The sine of pi on 4 is the y value, which is 1 on root 2. The cos of pi on 4 is the x value, which is 1 on root 2, because it's an isosceles triangle. We've used that to derive that. And the tan is interesting. The tan of pi on 4 is 1 on root 2 on 1 on root 2, which is 1, the y value on the x value. Now, this is better written as multiply top and bottom by root 2. You can get a simpler form. 1 by root 2 is root 2. Root 2 by root 2 is 2. And that's deemed to be the simplest form for what's called a surd, where you have a square root that's not exactly removable. So the square root of 2 is irrational, so we don't want to approximate it. So we try to get an integer denominator there, a whole number, and that's the way we do it. Multiply top and bottom by that surd, or that square root, and we get 2. Multiplying top and bottom doesn't change the meaning. So probably the best way of remembering sine and cos, pi on 4, is root 2 on 2. That is deemed to be the most simple or simplest mathematical form. Well, can we do this sort of thing for other angles? Okay, well, let's come down, and you know, back to the Babylonians, 360 degrees, we might want to do it for other angles. But here we have it, root 2 on 2 for pi on 4, and there'll be match-ups, won't there? There'll be match-ups. Remember what we did way back at the beginning. If we make two isosceles triangles here, so if that's pi on 4 and that's pi on 4, how far round is that? Well, this is pi to here, so pi take pi on 4, that is 3 pi on 4. That's what they're saying here. And that's going to have a match-up. The y's are going to be the same, the x value is going to be the negative. So we could say here the sine of 3 pi on 4 is a perfect match-up. It's root 2 on 2. The cos of 3 pi on 4 has gone negative in that quadrant. Remember, SATC, only sine is positive in this quadrant. So this is neg root 2 on 2. And we could say the tan is neg 1, sine over cos. So that would be 3 pi on 4. And we can keep this process going. Down to here, we again have a match-up. We've gone 5 pi on 4 because we've gone to pi there, and plus another pi on 4 is 5 pi on 4. So down in that quadrant, what can we say? The sine of 5 pi on 4 is the same, but it's negative, root 2 on 2. The cos of 5 pi on 4 is also negative. Only tan is positive down there, which is again then 1. A negative on a negative is a positive. And we can do this, we can have match-ups, if you like, equivalent in any quadrant. So if we go right round again to here, that's, if you like, 2 pi minus a pi on 4, or 8 pi on 4 minus pi on 4, 7 pi on 4. So the sine of 7 pi on 4 is negative. It's down in the negative y direction. The sine is the y coordinate. The cos of 7 pi on 4 is now back as a positive. It's root 2 on 2. And the tan of 7 pi on 4 is still 1, but it's neg 1. Okay, so the idea of having equivalent angles in quadrants due to these isosceles triangles we can draw in any quadrant. So you have equivalent positions. Just watch whether they are pluses or minuses here. And that's where this SATC helps remind you what is positive in each of those quadrants. All right, let's do another one or two. What about doing it for 30 degrees? So 30 degrees comes to here. Okay, 30 degrees, or pi on 6. Well, that arc length would also be pi on 6, wouldn't it, in the unit circle? And if we do a similar treatment there, and we're not going to do it now, it's getting a bit long, this presentation, we find that with pi on 6, the values are half and root 3 on 2. I suppose you could use trigonometry to check that. If you had 30 degrees, and that's 1, a half squared plus root 3 on 2 squared does give 1. Okay, 1 squared, which is by Pythagoras what it should be. So you could use that one there for pi on 6. 60 degrees is up here, and using that again, pi on 60 degrees or pi on 3, twice that angle, and they reverse. So here the cos is a half and the sine is root 3 on 2. Okay, and then of course you can do match-ups in other quadrants for each of these as well. Okay, match-ups right the way round. So the ones we want to remember now is that the pi on 6 angle has the sine of pi on 6 equal to a half, the y coordinate, and the cos of pi on 6 equals the x coordinate, root 3 on 2, and double pi on 6 is pi on 3, and its sine is the opposite way round. It's root 3 on 2, and its cos is a half. So they are the exact values. All right, let's come down and have a look at what that means. Here we have it. Here we have the matching positions, if you like. If you went to pi on 6 here, like that, it would match up with 5 pi on 6. Try to remember why, because this angle and this angle are the same. That's pi on 6 and that's pi on 6. You get match-ups, which means this angle here is 5 pi on 6, or the arc length, whichever way you want to think about it, because it's pi to here, and if you go back pi on 6, you have an equivalent position. So you must use this working angle. Think of the angle as a working angle, and you always have to work back from the x-axis. Working angle away from the x-axis to create the congruent triangles. Congruent triangles, which allows you to use symmetry, if you like, or showing you the symmetry of those of the unit circle, so you can have equivalent positions. So let's just check another one. Here we have pi on 3. If we go right round here to 4 pi on 3, that angle and that angle would be the same, and you'll have match-ups in the size of these, but not the sine. Because remember, as you change quadrants, SATC, the sine of the pluses and minuses, that is, of sine and cos and tan vary. Okay, so here's your method to matching up angles there. Alright, nearly at the end here, so I've made a summary. This is something that you really must memorise in the IB. They will give you many opportunities where you can use these sine, cos and tan values, but often in paper 1, and you won't be able to use a calculator at all. So you must memorise this table. It's what we've just done. Here the angles are across the top here, and then the sine and cos should be memorised. You can calculate this from those memorised values if you like, the tan values. They are not as important because you can work them from the others. Notice that I'm using root 2 on 2. Some textbooks use 1 on root 2. Pearson's use root 2 on 2 correctly because root 2 on 2 is the simplest third form. We don't keep a root in the bottom line here. We try to make that an integer denominator in third-land. Okay, so you need to memorise that. That'll take a bit of practice, but we can do it along the way. Alright, let's come down and have a look at some examples then. Find the following function values. Find the exact value if possible, otherwise find the approximate value. Okay, so the sine of 2 pi on 3. So you need to go pi on 3, there's your working angle. 2 pi on 3 would be pi on 3 back from the x-axis. Okay, so it would have the match up. It's a multiple of pi on 3. So find it, and then just adjust that one. That's got to be negative. The y's stay the same. The actual size of the values are the same, remember, because of the symmetry of the triangles or congruent triangles there. And so what is the answer? The answer for the sine of 2 pi on 3 is the y coordinate. It's that value there. Okay, let's have a look at 5 pi on 4 is in the third quadrant. How far past pi is it? It's pi plus another pi on 4, because pi is 4 pi on 4 plus another pi on 4 is 5 pi on 4. So the working angle back here is pi on 4. That's the one that would match up. And you know its values now, root 2 on 2 and root 2 on 2. So you want the cos over here of 5 pi on 4. So that is the x value of that 5 pi on 4, which is neg root 2 on 2. Okay, do you get the idea of these matching positions? 11 pi on 6, well 12 pi on 6 is 2 pi, so it's pi on 6 back from there. And when you see the pi on 6, you're thinking of multiples of pi on 6, so the matching one will be pi on 6 up here, which is root 3 on 2 for the cosine and a half for the sine. Now, what do we want here? We want the tan. So these values will be the same in size to these, due to that congruent idea. So we have the sine is neg a half, and the cos is root 3 on 2. So come over here. Neg a half over root 3 on 2, which is neg 1 on root 3. And you should multiply top and bottom by root 3 to get the simplest third form, which is root 3 on 3. 13 pi on 6 is more than one revolution, because 13 pi on 6 is 2 1/6 pi. So you've gone around 2 pi and then you start it again. So it's going to be the same as pi on 6. And so you can just use the sine of pi on 6 is a half. Okay, so the idea then is to map it out on a unit circle, match it up with a known point, and see how you go. The last little bit here, an arc length of 3.75, will have its terminal point in the third quadrant. What are they talking about here? Well, let's draw the unit circle here. And 3.14 is pi, so we know half a circle is pi, which is approximately 3.14. So 3.75 is down here in this quadrant. So what we know is here in this quadrant that we want the cosine it is equal to the x value, which is negative. So if we go to the calculator and put it in, we can check that its value is negative. Now, just checking on the calculator, we would go to setup mode, check that it's in radians, and then we can actually just hit cos in run mode of 3.75 and do it as we've done it before with trigonometry, because this time 3.75 is not a multiple of any of the known angles, so we know it's in this quadrant. So when we hit that, we just check that this is a negative. Alright, are you ready to have a go at some of these? Let's go down now, and this is just a set of all the problems, 22 now, 1 to 22, doing all the various things. Okay, question 1 is converting from radians to arcs and things like that from before, and seeing how you go. Alright, have a go at all of that, think back through it, pause presentation and start, and I'll just go down now and show you the solutions. Okay, so here's the first few, question 1 to 6. They haven't drawn diagrams. I think it would be good for you to draw a diagram to help you work it out there. Okay, questions 7 through 11 then. Question 12 through 16. Near there, 17, 18, 19 there. Twenty, 21. And then 22. Alright, well, a lot to remember there. Do your memorising work where necessary, and what we'll do is keep building an understanding of trig functions and drawing some graphs and stuff. I think you'll find it very interesting as we get into use them in modelling. But for now, it's cheers from me.